Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 10, Conducting a Simulation to Estimate the Probability of an Event. Conducting a simulation. Okay, what is a simulation? Okay, so I googled simulation for you and it says an imitation of a situation or process. Okay, so that's what we're going to do. We're going to imitate a situation. So in previous lessons, you estimated probabilities of events by collecting data empirically or by establishing a theoretical probability model. These are real problems for which those methods may be difficult, not practical to use. Simulation is a procedure that will allow you to answer questions about real problems by running experiments that closely resemble the real situation. It is often important to know the probabilities of real-life events that may not have known theoretical probabilities. Scientists, engineers, and mathematicians design simulations to answer questions that involve topics such as disease, water flow, climate changes, or functions of an engine. Results from the simulations are used to estimate probabilities that help researchers understand problems and provide possible solutions to these problems. Okay, so example 1. Families. How likely is it that a family with 3 children has all boys or all girls? Let's assume that a child is equally likely to be a boy or a girl. Instead of observing the result of actual births, a toss of a fair coin could be used to simulate birth. If the toss results in heads, H, then we would say a boy was born. If the toss results in tails, T, then we would say a girl was born. So heads is boys, tails is girls. If the coin is fair, for example, heads and tails are equally likely, then getting a boy or a girl is also equally likely. Okay, so exercise 1 says, suppose that the family has 3 children. To simulate the gender of the 3 children, the coin or number cube or a card would need to be used 3 times, once for each child. For example, 3 tosses of the coin resulted in heads, heads, tails, representing a family with 2 boys and 1 girl. Note that heads, tails, heads, and tails, heads, heads also represent 2 boys and 1 girl. So number 1 says, suppose that when a prime number P is rolled on the number Q, it simulates a boy's birth, and a non-prime composite, by the way, simulates a girl birth. Using such a number Q, list the outcomes that would simulate a boy birth and those that simulate a girl birth after the boy and girl birth outcome. Are the boy and girl birth outcomes equal? Okay, so we have a die with 6 sides. So if I roll a 2, that's prime. If I roll a 3, that is prime. And if I roll a 5, that is prime. So if I roll any one of these, that will equal a boy. Okay, if I roll a 1, or a 4, or a 6, that would be a girl. Remember, 1 is not a prime number. 4 is 2 times 2, 6 is 3 times 2, so they're not prime. So we have the probability of getting a boy would be 3 out of 6. The probability of boy would equal 3 out of 6. The probability of a girl is also 3 out of 6. So are the boy and girl outcomes equally likely? The answer is yes. They're both 50-50 chances. Number 2. Suppose that one card is drawn from a regular deck of cards. A red card simulates a boy. A black card simulates a girl. Describe how a family of 3 children would be simulated. Okay. In this situation, you have to know about decks of cards. There's hearts, there's diamonds, there's clubs, and there's spades. Hearts and diamonds are red, clubs and spades are black. Every suit, which is what they're called, has 13 cards in it. So there are 26 spades and clubs combined, 26 hearts and diamonds combined. So there's 26 red and 26 black cards. Okay? So now we want to simulate this. A red card equals boy. A black card yields a girl. Okay? Okay, this was a lengthy answer, so I just brought it in and typed. The key response has to include the drawing of 3 cards with replacement. If a card is not replaced and the deck shuffled before the next card is drawn, then the probabilities of the genders have changed. Ever so slightly, but they are not 50-50 from draw to draw. So we have to simulating the genders of 3 children requires the cards to be drawn with replacement. We draw it, we put the card back in, we shuffle, we draw. Okay? Example 2. The simulation provides estimates for the probability that a family of 3 children would have 3 boys or 3 girls by performing 3 tosses of a fair coin many times. Each sequence of 3 tosses is called a trial. If a trial results in either 3 H's or 3 T's, then the trial represents all boys or all girls, which is the event that we are interested in. These trials will be called success. If a trial results in any other order of H's and T's, then it is called a failure. The estimate for the probability that a family has either 3 boys or 3 girls based on the simulation is the number of successes divided by the number of trials, which we did in earlier chapter section. Introduce that in 4. Suppose 100 trials are performed, and that in those 100 trials, 28 resulted in either 3 H's, 3 heads, or 3 tails. Then the estimated probability that a family of 3 children has either 3 boys or 3 girls would be 28 out of 100, or 0.28, or 28%. Okay, so now exercise 3 through 5. Number 3 says, find an estimate of the probability that a family with 3 children will have exactly 1 girl using the following outcome of 50 trials of tossing a fair coin 3 times per trial. Use H to represent boy and T to represent girl. Okay, so they've given us this estimated trial, that is an estimate. They did a random trial, and so here it is, and we want to know what the probability, so T represents girl. So what does it say? Find the probability that the family of 3 children will have exactly 1 girl. We want exactly 1 girl. So we have to let T equal girl. Now we're looking for any one of these that just has 1 T. There's one, no T's. 2 T's is not exactly 1 T. Skip it because it's 2, 2, 0, 2, 0, or 0, 1. There's 1 T. 3, 1. Just looking at 1 T. Okay, here's 1. 1. 3, 2, 2, 2, 0, 1. 2, 1. 3, 2, 0, 2, 2, 1. 1. 0, 0, or 0, 0, or 3 tails, 2 tails, 2 tails, 1. 2, 1. 3, 0, 1. 1. 2, 2, 3, 1. 1. 2, 3, 2. Okay, so I just circled all the possible outcomes where there was only 1 T in the 3 tosses. So then I would take those and count them and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the probability of 1 T, okay, let me just call it probability of T, equals 16 out of the total number of trials. We were told it was 50, and this is a row of 10, and there's 5 of them, so the probability that we would only have 1 girl would be 16 out of 50 attempts, which would be 32%. So there's a 32% chance that we will have exactly 1 girl. Number 4. Perform a simulation of 50 trials by rolling a fair number cube in order to find an estimate of the probability that a family with 3 children will have exactly 1 girl. Specify what outcomes of 1 roll of a fair number cube will represent a boy and what will represent a girl. Okay, so since there are so many possible outcomes, I just brought this in, and it says answers will vary. For example, students could identify a girl birth as 1, 2, 3 outcome on the die, or roll a number cube 3 times, simulate 3 children on one trial. Okay, or they need to list their 50 trials. Okay, so we could use 1, 2, and 3 for a girl, and roll it 3 times, and list that 50 times. Note that an outcome of 4, 1, 2 would represent 2 girls and 1 boy, because the 4 is not a girl. 1, 2 is a girl, 4 is a boy. So 1, 2, 3 would represent 3 girls, and 3, 6, 6 would represent 1 girl, as would 6, 3, 6, and 6, 6, 3, because 6 is a boy. I'm sure that they are clear about how to do all 5 steps of the simulation process. Okay, so what did we do? We assigned 3 numbers on the die to girls, and then we did 50 rolls, 3 rolls per 50 attempts, so it's really 150 rolls. Roll it 3 times, that's 1 trial. Okay, so B says to simulate 50 trials. Keep in mind that 1 trial requires 3 rolls to the number cube. List the results. You list the results of your 50 trials. Okay, so if you were to do this on your own, this would take a little while. You would have to have a die. You'd have to roll it 150 times. And you would get an outcome similar to this here. That's what your trial should look like if you actually did this. Okay, and then calculating the estimated probability, however many times that occurred, divided by 50. Okay, so I'm going to just move on now. Calculate the theoretical probability that a family with 3 children will have exactly 1 girl. List all the possible outcomes for a family with 3 children. For example, one possible outcome is BBB. All 3 children are boys. So the sample space is, for 5, we need a sample space, and that would be boy, 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 or boy, boy, girl, or boy, girl, boy, or girl, boy, boy. So notice what I'm doing here. I'm starting with all boys. I introduce 1 girl to this 3, and it's got to be here, and then I just moved it to the 2nd position, and then to the 1st, and moving these out of the way and just rearranging. And then once I've done that, now I've got to have one possible outcome where there is a boy first, and then a girl, and then another girl. Okay. Now I'm going to move the B throughout, so it's going to be G, B, G, and then finally G, G, B. And then, so we have 3 boys, 2 boys and a girl, all 3 possible outcomes, 2 girls and a boy, all possible outcomes. And finally, we round it out with 3. That's the easiest way to do this without skipping or missing it or repeating it. B says assume that having a boy and having a girl are equally likely. Calculate the theoretical probability that a family with 3 children will have exactly 1 girl. So all I have to do is look up here in my sample space, and if it's all equally likely to occur, then this would be a failure. Remember what they said? You either have success or failure. So our success would be family with 3 children will have exactly 1 girl. So this is a failure. This is a success. This is success. It's just 1 girl. Success. Success. 2 girls is a failure. 2 girls is a failure. 2 girls is a failure. And 3 girls would be considered a failure if we want exactly 1. So here are our 3 successes. So the probability of exactly 1 girl is 3 out of our total of 8 outcomes. So the probability of 1 girl equals 3. Compare it to the estimated probabilities found in parts A. Okay, so that is going to be on your own, because if you didn't do that, then you have nothing to compare it to. Since it was multiple outcomes, I didn't do those, so we're going to continue. Example 3, the basketball player. Suppose that, on average, a basketball player makes about 3 out of every 4 shots. In other words, she has a 75% chance of making each foul shot she takes. Since a coin toss produces equally likely outcomes, it could not be used in a simulation of this problem. Instead, a number cube could be used by specifying that the numbers 1, 2, or 3 represent a hit, number 4 represents a miss, number 5 and 6 would be ignored. Based on the following 50 trials of rolling a fair number cube, find an estimate of the probability that she makes 5 or 6 foul shots she takes. So if you look in here, we only have 1, 2s, 3s, and 4s. 5s and 6s were ignored. We also could have used that tetrahedral die of 4 sides. We wouldn't have to ignore any. Every side would be used. But anyhow, those aren't as common as a regular die. So here's our outcomes. So it says find the estimate of the probability that she made 5 or 6 of the 6 foul shots she takes. So we want 1, 2s, and 3s. 4 represents a miss, so we only want 1 4 or no 4s. So 5 hits equals 1 4. Okay, 6 hits equals, oh wait, not 6 hits. So what are we trying to do here? Okay, so 5 hits, we would only have 1 4. 6 hits, we want 5 or 6 hits, would equal 0 4s. Okay, so we're looking for 1 or 0. So there are 2, so I'm not going to use that. There's 2 here, so I won't use that. Here's 2. Here's 1, so I will use that one. So there's 1. Okay, this one has 2, so I won't use that. Okay, that one has 3. So that was only 3 hits. This one was 4 hits. We want 5 or 6. There's 1 4. So there's a 1 2 2 3 2. So that is 5 out of 6, and so on. 2 3 2. There are no 4s here, so that was perfect 6. Here there are 2 4s, so I'm not going to use that. Okay, 1 4 1 4 1 4 1 4. 2 3 4s, so I won't use that one. So I will use this one, and this one, and this one, and this one. Okay, this one has 2, so I'll skip it. 2, skip it. 1. Perfect. Perfect, no 4s. 1 4 is okay. 2 4s is not. 1 4 is 5 hits. 5 hits. 5 hits. 2 is only 4 hits. 2, 2, 2. Here's 1 4. And so on and so on. This is what we do. I'm looking for all the groups of numbers that only have 1 4, and that is not 1. So I've got to, there's 2 there, skip it. This one there is 1. There's only 1, no, there's 2 4s here, so I got to skip that. This was a perfect 6. 6. There's 2 there, only 1 here, 1 here. Hang in there with me. There's 1, 2, there's 1. 3, no. 2, no. All 6. All 6. 5 is good. 3 is not. And 5 is good. Phew. Okay, so now what we need to do is count these. There are 50 trials. 1, 2, 3, 4, 5, 10 rows of 5 columns is 50. So now I just need to count the red circles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 4 is 14, 15, 18, 19, 20, 21, 22, 23, and 4 is 27 out of 50. 4, 54.54. Okay. Okay, so that is the end of lesson 10. Go to your problem set.